let's go ahead and dive into example 3. We want to compare drive-through wait times at 2 different restaurants, Wendy's and McDonald's. Just from reading that, my quantitative variable is going to be wait times, and my categorical variable with 2 options, creating my group, is going to be Wendy's and McDonald's. We took a random sample of 35 wait times at each of the restaurants. We found the mean wait time at Wendy's, given their information. Same thing at McDonald's. We're going to construct a 98% confidence interval. Now, since we just discussed the idea of working with independent samples, you can guess that this is going to fall into that category. However, let's first go through and make sure we know why they are independent samples. Now remember, we always assume they are independent until we know otherwise. So it says we took a random sample of 35 wait times at each of the restaurants. So if I sampled a certain person at Wendy's, do I now know I have to sample a certain person at McDonald's? Not from what's given, right? So if you need to, you can draw out those little pictures to help you understand it. So if Sally was chosen at Wendy's, that doesn't tell me anything about who might be sampled at McDonald's. There's no known reason to match the person at Wendy's to a person at McDonald's. So again, this is where knowing that they're independent until we know otherwise will be important for us. Other things I'm going to go ahead and list here that we know about Wendy's and McDonald's. For Wendy's, we were given the mean to be 109 seconds. The standard deviation of the sample, because it was just of those 35 times, was 14 seconds. And they sampled 35 people at Wendy's. Now at McDonald's, the sample mean instead was 125 seconds. The sample standard deviation there was 25 seconds. And they also sampled 35 people at McDonald's. All right, so let's go through our steps for constructing our confidence interval. So step 1 is to always get our parameter of interest. So I'm going to do my order of subtraction as Wendy's minus McDonald's. So I'm going to use little W and M subscripts to help me out. So I'm going to do the mean of Wendy's minus the mean of McDonald's. So what this means then is that I'm finding the difference in population mean drive-through wait times. Of Wendy's and McDonald's. Unit-wise, where things were measured in seconds. But let's also take a moment to think about what it would mean if I got a positive number, a negative number, or 0. So if my order of subtraction is Wendy's minus McDonald's, and I get a positive number, the first value has to be bigger than the second. So Wendy's would have the larger time than McDonald's. If I got a negative time, Wendy's would have a smaller time than McDonald's. And if we got 0, that would mean that they were equal. Now looking at the values that I got over here, our sample mean for Wendy's was less than it was for McDonald's. So I'm going to already feel like I'm going to be getting some negative numbers. And negative numbers are okay since we're looking at a difference in mean wait times. Our second step is to check our conditions. Now we sort of drew pictures over here to explain them being independent, but let's actually now write that down in our conditions. So the reasoning why we have independent samples is again that there's no known reason to match the customers at the 2 restaurants. Right, still were they done randomly? Well, it says they took a random sample of 35 wait times at each restaurant. So again, at least from what I know, there was no known bias going on there. Now for both samples, we either need to know that the population they came from was normally distributed, or have samples of at least 30. Now again, to assess if things are normal, if we had histograms to look at, we could see if they were symmetric and unimodal. Those were not provided here. Or it could say in the problem that we could say that the population wait times were normally distributed. Does not say that here either. So we do not know that they are normally distributed. Now, luckily, we do have samples of at least 30 for both of our groups. So we have our mean for Wendy's was 35, and our sample size for McDonald's was also 35. So they are both met here. So we're good on that condition. Finally, we need both of our population standard deviations to be unknown. And again, the main reason for that is why we're using the t-distribution. So that's true. We have our sample standard deviations instead. Alright, so on step 3, we're going to be doing the calculation of the interval, but we're going to be utilizing a lot of StatCrunch output to help us here. So going back and forth, looking at the formula here, the y bar 1 minus y bar 2 isn't going to be too hard for us because we already have those two numbers. So I'm just going to go ahead and write everything out here. So we're going to take the 109 minus the 125 plus or minus a t, which we'll come back to fill in, times this big square root. Now for that, I need each of my standard deviations and my sample sizes. So my standard deviation for each group and my sample sizes that I'm going to plug in to this formula. So each of the standard deviations gets squared, and then both of them have the same sample size of 35. Now how I can get my t is based upon my confidence level, so it told me to be 98% confident. But then I also need my degrees of freedom. You'll notice down here in the StatCrunch output that degrees of freedom are given to us. And at this point, you may be able to see why you're not calculating this by hand. Generally, our degrees of freedom has been a whole number, and that's not the case when we're working with two independent samples. So we're going to use that to help me find my t. So I'm going to use the fact that we're 98% confident, and for my degrees of freedom, I would like to try to use 53. So let's pull up our table and look at that first. So here's my t-table. Here's that 98% confidence. And then I'm going to try to scroll down to where I can find 53 degrees of freedom. And you'll notice again that we do not actually have 53. Now from my point of view, if you use either 50 or 55, I'm perfectly okay with that. I will always round down my degrees of freedom because I'd rather underestimate my sample size instead of overestimate it. So for that reason, I'm going to choose the 2.403 to be my t. So I rounded down to 50. So now I can take that number and put it up here in my formula. Now, could you do this math? Yes, it may take a little bit of time, but you could do it. But let me kind of write out the next pieces so you can see where other values of StatCrunch are useful. So if I take 109 minus 125, I get negative 16. Notice how that value is actually down here in that StatCrunch output. T is not given to me in a confidence interval, so I have to actually use that number. If I found this entire square root, Recall that's another name for standard error. So we're actually given this number, it's 4.843. So instead of doing all that math, which again isn't necessarily hard, but lots of little things could go wrong, especially maybe in a testing situation, I can just utilize that StatCrunch output to help me. From here, I would hope that you could do the math. So let's write out what that math would look like fully. So I'm going to take negative 16 minus my t times my standard error, and then take my negative 16 plus my t times my standard error. And so now the math isn't too bad. I just need to do my multiplication first. And then finally my subtraction and addition. So there's the math done for us utilizing the StatCrunch output to help us. Notice how you also will see numbers similar to that, not exact, as the lower limit and the upper limit. Now, why do these numbers not turn out exact? Well, one of the biggest reasons why they're not exact is because what happened here with me with that t. I couldn't find exactly 53 degrees of freedom. I had to use something a little bit different. Versus when StatCrunch does it, it has an unlimited table, so it's not restricted like we are. So the values are close, but not exactly the same. All right, finally, we're going to want to interpret this interval. But let's go back and remember what our values mean, because you'll notice our entire interval has negative numbers in it. So all negative numbers mean is that Wendy's wait time then is less than McDonald's. So this being all negative, when I'm doing my interpretation, I'm going to be wanting to say that Wendy's wait time then is less than McDonald's. So now let's put that all together in our interpretation. So we always start with how confident we are. So I am 98% confident that our population mean drive-through wait time at Wendy's, since it was my first thing listed, I'll write it first, is, I'm going to come back and fill this in, is less than at McDonald's. Generally, we feel pretty good about saying that it's less at Wendy's than at McDonald's. Now, what am I actually going to fill this in with is the actual, well, how much less? Now, the numbers I'm going to use here will be similar to what you see up here, but not exact. Now, why not exact? I don't want negative numbers in my interpretation. And all the negative really told me was that Wendy's was less than McDonald's. And I've already said that. So now that I've said that, I can pretty much pretend that those negative numbers are not there. And then I'm just going to put them in the order that makes more sense. So I'm going to say is between 4.362 and 27.638 seconds less than at McDonald's. Now, these interpretations can take a little bit of practice, but understanding that sign and taking care of that early here before you let all the numbers possibly confuse you can be very helpful for students. So again, so negative numbers here are okay because we're calculating a difference between two things. In the next video, we'll just show you how to get the StatCrunch output that you saw here.